Here shows that how to make a Fourier transform for periodic signals. We know that the delta function of this one in the frequency domain, it looks like this one. It's only non-zero, omega equals omega 0, and that's the 2 pi times delta omega minus omega 0. So if it is given, then we can take in inverse Fourier transform of that. Inverse Fourier transform can be taken by the 1 over 2 pi and taking integration minus infinity to infinity, and this one delta function 2 pi times delta omega minus omega 0 and e to the j omega t d omega. By taking integration of this one, only omega equals omega 0 is non-zero, so we can replace omega with omega 0 and 2 pi is cancelled out. Then xt is given by e to the j omega 0 t. So we know this one. Then if xj omega is of impulse spectral, here shows that 2 pi times delta omega minus omega k0, and this is the coefficient. This one seems like if this is omega, and each one has 2 pi times ak magnitude and delta function at the k times omega 0. This one is a case harmonic component 2 pi times ak. So this one shows that the harmonic component of that one. In that case, we can take inverse Fourier transform by the same techniques as we have proved here. And then in these cases, it's given like a complex exponential sum. Okay, xt is a sum of the complex harmonic exponential. So this is Fourier series expansion. We know that this one is Fourier series, and Fourier series signal always periodic. So periodic signal can be expressed by the sum of delta pulse train. Here shows another impulse pulse train. Xt is an impulse sequence. At every t is impulse exist. So this one obviously of periodic signals. So we can express this impulse train with sorry, this one should not be here. This signal can be expressed by the Fourier series expansion. So to figure out this Fourier series coefficient, we can take in integration for here. So over one period, we take the integration for case harmonic component by using this integration. Then regardless of the k value, it always 1 because of this delta functions 1 over t. So we can express the same signal with in this Fourier series expansion, and then taking the Fourier transform. We know that the complex exponential can be converted to 2 pi times delta function by use of these techniques. So we can make a Fourier transforms of this impulse train. This impulse train is time domain, is impulse. It's a unit impulse at this moment. This one is unit impulse at every t. After taking the Fourier transform, it has another pulse train. You know that this one is a impulse trains. At every case harmony, it has impulse. The magnitude is scaled 2 pi over t. So this should be 2 pi over t. Okay, 2 pi over t and every omega 0. So this is impulse train for the Fourier transform of this one. So carefully watch the impulse train, and then taking the Fourier transform, it gives another impulse train, but the scale factor is different. If it is unity, it is 2 pi over t. Okay, and here is another example. If in time domain is impulse, it means that this is time and signal is impulse. Magnitude is k. Taking the Fourier transforms, then in the frequency domain, it's a constant k. All the frequency, it is always all value is k. It's a constant over the omega. So by taking the Fourier transform, t equal 0 has non-zero value, so we can replace that one. That gives k. So we can know that the inverse Fourier transform of this one in the frequency domain is a constant, then it should be impulse in the time domain. The inverse Fourier transform can be taken from here like that. 1 over 2 pi times integrations minus infinity to 50 by infinity with a constant k, and inverse Fourier transform are defined in this way. It should be this impulse response k times delta t. Okay, we by use of this inverse Fourier transform we can prove that minus infinity to infinity e to the j omega t d omega equals to 2 pi times delta t. Similarly, we can place t and omega. It should be the same. It means that the k and up to e to the j t omega zeta dt. Okay, this also should be 2 pi times delta omega. Okay, you think about just the replaced t and omega. Okay, just to change the variable. Still that omega changing minus infinity to infinity, and similarly t changing minus infinity to infinity, then it should be satisfy this one. So by use of this one we can prove that in case of a constant in the time domain, if signal at this moment we assume that the signal is constant k in time domain. So what is the Fourier transform of that one? To prove that one, we need to refer this result. The Fourier transform can be taken by integration from minus infinity to infinity, and k times e to the minus j omega t dt. But at this moment you know that this one is a real number, so taking conjugate it doesn't change, so it's the same thing. So by use of this one we can prove that the 2 pi times k times delta omega is this one. So in the time domain is constant, then in the frequency domain it's impulse. Magnitude is 2 pi k. This is 0. So here shows that if time domain is impulse like that, then the frequency domain is constant over frequency. But if it's a constant over time, then it's impulse at t equals 0. It's a scaling factor is 2 pi times k. We proved that one. Next one, we will talk about the property of Fourier transforms. We know that the Fourier transform definition and also its corresponding inverse Fourier transform are defined in this way. We call this is in Fourier transform pair. Xj omega is Fourier transform, xt is time domain, expression is a inverse Fourier transform of that. First, Fourier transform satisfy linearity. We know that a Fourier transform can be done, and inverse is the same by taking integration. Differentiation and integration satisfy the linearity. Linearity means additivity is preserved and a scalability also are working like that. So Fourier transform satisfied linearity property. Additivity and also scalability is satisfied because that's the linear operator. And another one is time shifting. If we're taking Fourier transform of xt minus t0, it's a shifted version of the signal, and taking the Fourier transform it will give, you know, that if you replace this one with tau, and dt equals to tau minus, okay, dt equals to d tau. Okay, just replace tau as a t minus t0, then xt minus t0, I replace the xt minus tau, and t, you know that if we tau equals to t minus t0, then t equals to tau plus t0. Then we can replace this t with this value, then it will give e to the minus j omega tau, and t0 are given here. dt replaced by the d omega, so d tau, okay, d tau, tau changing minus infinity to infinity if t goes minus infinity to infinity. So we can write down in this way. Then from here, the Fourier transform of the shifted version is xj omega, that's this part, times e to the minus j omega t0. So this is shifted value. It just is changing the phase of the xj omega. So phase changing depending on the omega times t0. Okay. The third one is time and frequency scaling. In the frequency scale, the time scaling is this one. If x a times t, a can be positive or negative. Firstly, we assume that a is a positive number. Okay. Then xt is given like this way. Fourier transform is given like that. From here, we can replace at as a tau. Then dt equals to a to the d tau. We need to assume that a is positive. Then tau will changing from minus infinity to infinity. You know that we assume that the t changing minus infinity to infinity. Then tau will changing, in case of a is positive, minus infinity to infinity. What if a is negative in this case? A is negative case. If t changing minus infinity to infinity, then tau will changing. In case of minus infinity, because it's negative, it's positive infinity. To t goes to the, this one represents the t variable. Then it should be minus infinity. So integration is changed. So we always taking integration from minus infinity to infinity. So minus infinity to the infinity, in case of a positive case, we can just integrating that one. And t at this moment is a tau over a. So t is replaced by tau over t. So we can tau over a, it can be replaced by this way. It's the same thing, but at this moment it's changing infinity to minus infinity. So we switch the integration direction minus infinity to infinity and give a minus in case of a is negative. So the later part, this part or this part, corresponding to Fourier transform of this one. You can think about the omega is changed omega over a. So this one is original Fourier transform of xt. And what about the scale factor a? In case of positive is 1 over a. In case of negative, it should be minus 1 over a. So we can taking absolute value of that. Okay, so we can understand the time scaling factor will be replaced, expressed in this way. What about in this case? We know that xt Fourier transform is xj omega. Is xj omega. Then what is Fourier transform of reverse signal? When we take the reversed signal, then the Fourier transform will looks like this one. In this case, a is minus 1. A equals minus 1. So absolute value is 1. Here shows minus a. So we can replace omega with minus omega. Then it gives the reverse signal of that one.